from the positive side to the negative side, and that particular I is nothing but the conventional current flow in that particular circuit. The temperature of a substance changes or the conditions of temperature change in your experiment, then the resistance value will not be a constant. It will fluctuate and Ohm's law will not hold. This is a device which offers resistance in a circuit, and that particular resistance offering device is known as a resistor. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about current, electricity and its properties. We saw how electrons get accelerated inside a conductor and how to calculate its average velocity, current density, and how to calculate the current flowing through that particular conductor in a sort of quantum mechanical way. Now we are going to deal with Ohm's law. So what does Ohm's law actually mean? We have seen that several times in your lower classes, so we are going to take a closer look at Ohm's law. So in the previous class, we discussed how we can actually derive Ohm's law and how we can find the relation between V and I. So from that, we know V is directly proportional to I. That is, voltage is directly proportional to current flowing through a conductor. That is, if I have, let's say, a conducting material like this connected to a battery of V volts, and there will be current flow because of the potential difference between the 2 points. So this will be positive and this will be negative. So obviously there will be current flow. Current I will be flowing from the positive side to the negative side, and that particular I is nothing but the conventional current flow in that particular circuit, but the electron flow will be in the opposite direction known as electronic current. But anyways, so the point is that if I am using 1 volt of battery, that is, I'm using a 1 volt battery to power this particular circuit, and I was getting an output of 1 ampere. So let's say 1 milliampere. For simplicity's sake, let's say I'm getting a 1 ampere current output. So I can say that when I increase this particular voltage, let's say to 5 volts, then the current was also found to be increased by a factor of 5. That is, if I increase the voltage to 5 volts, the current output was also found to be 5. It does not essentially have to be equal. If I get 1 here, it can be 0.5 here. If I get 5 here, it can be 25 here. The point is that as I increase the voltage value, the current value will also go on increasing. That is, if I plot a graph, let's say against V against I, that is, in the experiment I am doing involving voltage and current, I plotted a graph with voltage against current, and I'm going to plot each value there at particular times. When I introduce the voltage of 1 volt, then I got a current value of 1. So this was the value that I got. Let's say this was 1 and this is also 1. And after some time, I introduced the voltage of 5 volts. Let's say this is 5 volts. Then automatically I got the current output also to be 5. So which means that the current output was also 5. Just like that, I plotted even more values with increasing amount of voltage and respective current values. So as I increase the voltage values, the I value also was found to be increased proportionally, directly proportionally. That is, if I took voltage 5, current was 25. If I took voltage 10, the current was 100. Just like that, current also went increasing as I increased the voltage, and the values was found to be in an increasing manner. So when I plotted a graph, the graph was found to be a straight line. So this particular relation proved that, or this particular experimental setup proved that V was directly proportional to I. So I can say that V is directly proportional to I. And this was found out by G.S. Ohm, a physicist who was researching the relation between voltage and current. So, and out of respect for him, we use his name as a unit of something which you will see very soon. So we can say that V is directly proportional to I, or we can directly just say that V is equal to IR. This particular R is known as resistance. So what exactly is resistance? How is it affecting this particular circuit and how is it behaving in general? All that will be seen very soon, but for now just know that Ohm's law is nothing but V is directly proportional to I. Or in a clearer, more precise sentence, I can say that the current flowing through a conductor, that is, if this is the conductor, the current flowing through a conductor will be directly proportional to the potential differences across that conductor, given that the temperature remains constant. So, at constant temperature. So you can say that Ohm's law only holds true when the temperature is unchanged. That is, if the temperature changes, then the value of resistance will also change and this relation won't hold. So we can say that the potential difference between the two ends of a conductor will be directly proportional to the amount of current flowing through that particular circuit at constant temperature, and that relation is known as Ohm's law. And we can say that the proportionality constant introduced between I and V is known as R, that is resistance, and the unit of resistance is nothing but ohms. Or we can just say that mathematically R is equal to V by I. So this is just a mathematical relation. Don't take into account for the physical significance. Don't think that just because this mathematical relation exists that I and R are inversely proportional. That is not the actual case. That is not how you should read that particular equation. The point is that this is a mathematical relation where V by I will give you the resistance. But in actuality, it is not. R is inversely proportional to the amount of current flowing through that. That is not the sense you should take in. So just a heads up. That is the initial considerations you have to remember. But if you remember the last class, we proved Ohm's law, which stated that V is equal to L by sigma A into I. This was the result we derived in the last class, and we could say that this particular quantity is now known as R, or resistance. So in the equation V directly proportional to I, or V is equal to IR, this particular R is nothing but this particular quantity. That is, resistance depends upon the length, area of cross section of the material and conductivity of the material. But resistance is inversely proportional to the conductivity of the material. That is, if R is equal to L by sigma A, then we can say that we can derive the relation that resistance is inversely proportional to 1 by sigma, inversely proportional to 1 by A, and it is directly proportional to length of a material. So we can say that essentially, if we increase the length of a material, the resistance of that particular material is double. If we increase the length of a particular material, then the resistance will also be increased. And if we increase the area of that particular material, then we have to say that the resistance will go down, as they are inversely related or inversely proportional. And finally, resistance is also inversely proportional to conductivity, that is 1 by sigma. And this particular 1 by sigma, that is 1 by conductivity, is also known as resistivity. So we can say that 1 by sigma, that is 1 by conductivity, is equal to rho, that is resistivity. So 1 by conductivity is equal to resistivity. How much resistance can a material offer depends on the inverse of its conductivity. Conductivity was how much easily can a material let charges through that, and the opposite or the inverse of that is resistivity, how much a material can resist the flow of charges in them. So 1 by sigma can be written as rho, so it can arrive at the relation that R is equal to rho L divided by A. And this is a particular relation you have to remember that affects resistance of any material. That is, resistance is directly proportional to resistivity and length, and it is inversely proportional to the area of cross section. What does it actually mean? We'll get that to it immediately. Just before going into further detail, just remember that Ohm's law states that V is directly proportional to I, that is, potential difference across a conductor is directly proportional to the current flowing through that conductor, given that the temperature is constant. And the graph between V and I will always be a straight line. From the previous derivations, we arrived at the conclusion that resistance of a material is related to the resistivity, length and area of cross section of a material, which we can look further into it and we can arrive at an even more simplistic conclusion. So what exactly are resistors? In your labs, you might have seen a number of these materials which has different color rings on them. This particular material is known as a resistor. They can be of different values depending on the color code that is arranged in them. We will talk about them a lot in the coming classes. Just for now, just take a look at them, and these are known as resistors, and they can be of different values. They can be of 500 ohms, they can be of 1000 ohms, they can be of 2 kilo ohms. Like, the values can keep on changing. Point is that these are known as resistors. They offer resistance to the flow of current in a circuit, and the symbol for resistance is denoted as such. It's like a few curvy lines drawn like this. This particular symbol will give you the resistance in a circuit. That is, if you're drawing a circuit that, let's say this is a bulb, then I can see that this particular quantity is the resistance. That is, this particular symbol denotes resistor connected in this particular circuit, and that particular thing, that is, the resistor, is this particular thing. So this is a device which offers resistance in a circuit, and that particular resistance offering device is known as a resistor, and they are of different categories and of different magnitudes and values. So what exactly is resistance? A little more clearer explanation was yet to be given. So I can just say that if you consider a material, let's say this is a material which has a length L and an area of cross section A. So this particular material has a length of L and an area of cross section A, which is connected to a high voltage battery, that is V. It has V volts. So we can say it has V volts, and it offers current flow into the material which we have just connected. And I is the amount of current flowing through that particular circuit. Then I can say that the direction of current flow in this particular material is in this direction, that is, I is flowing in that particular direction, but the electrons are experiencing a force in the opposite direction. In the opposite direction, all was seen before. And now the important factor, we just saw that current and voltage are directly proportional, which means that if I increase the voltage, more amount of current will be flowing through that particular material. And resistance is a quantity that is in between current and potential difference, that is current and voltage. So what does this resistance exactly do? So what do you think the word resistance mean? Resistance means that it opposes something. In this particular case, the resistance is the opposition or restriction offered to the flow of this particular current. So if you imagine that this is a tap, this is a tap through which water is coming out, and I have connected a hose to it so that I can spray water anywhere I want. So what I did was, I have a nephew who's very naughty. So what he's doing is that he pinched, that is, he pressed on the hose so tight that water was not flowing properly. So water is not coming out easily as expected. Only drops were coming out. So I know the reason why. It is because somebody is obstructing the flow of water in this particular pipe. That is, my nephew is applying a force so that this particular flow of water is obstructed. Just like that, when current tries to move freely through a material, its free motion, that fluid motion, is opposed by something, is opposed by an entity. That particular entity is known as resistance. For example, when we walk in a rough road, friction acts against us. That is, friction offers a resistance to fluid motion. Just like that, in the case of flow of current, resistors offer resistance, or anything in the material of the substance we are using will offer a certain amount of resistance so that current cannot easily flow through that. And we are going to measure that particular resistance. If you still want a clearer picture, you can imagine voltage as the guy who's pushing someone across. That is, current is the guy voltage is trying to push across a certain space. But resistance is the guy who's trying to push him out. That is, who is pushing in the opposite direction. So voltage is trying to push the guy to the other side. That is current. And the resistance offered in this particular material is the guy who's trying to not let him through that easily. So that is how the picture should be in your mind. Resistance is opposition to the easy flow of current through any material. And it does not have to be a resistor which is introduced, because innately many substances will have resistance on its own. The level will only vary, but resistance is innately within every substances when current is flowing through them. That is why when current flows through a copper wire, we can take the example of a copper wire. When current flows through a copper wire, you can experience heat from that copper wire. If you are charging something, if you go ahead and touch that charger after some time, you can feel heat coming out of it. That is because the resistance offered by the copper wire is blocking the current from efficiently passing through that particular copper wire. That is why it gets heated up. That heat is particularly a byproduct of, or it is the heat developed is due to the reason of resistance. So just now I told you that resistance was dependent directly upon length and inversely to its cross-sectional area. That is, if I increase this particular area, if I make it double, that is 2A. If I make the cross-sectional area 2A, then automatically this area will be doubled, which means that they are inversely related, which means the resistance will go down. So it will be more easier for charge carriers to pass through that particular area. Imagine that only one person or one electron could walk through this particular door. If I increase or made the door size even larger, then a number of soldiers could easily walk through that, or a number of electrons could easily walk through that. Then I can say that if area is doubled, the motion through it will be easier. So that particular relation is also applicable here. When area is doubled, resistance goes down. Resistance is the opposition offered to that particular flow, so that will go down as area is doubled. Now what happens when length is doubled? When length is doubled, that is length becomes 2L, then it is an increase in the numerator, which means resistance is directly proportional to length. If length is doubled, then resistance is also doubled. Imagine that particular electron now has to travel even more distance across this rough environment, which means that the resistance is even more right now. So it was like crossing a small desert once, and now it's like crossing a larger desert right now. So that is the difference. The resistance is directly proportional to L. If you increase the length, then the resistance will also increase. It will be that much difficult to cross that particular region, depending on the substance used. So this R directly proportional to L by A can be written as introducing a proportionality constant, that is rho L divided by A, And we just saw that this rho is nothing but resistivity. So this rho is nothing but resistivity, and rho can be written as 1 by sigma. It's a dimensionless quantity and it can be written as 1 by sigma, or inverse of conductivity is resistivity. So R can be written as R is equal to rho L divided by A. So we can actually substitute this equation into the equation for Ohm's law, and we can write it as V is equal to rho L divided by A into I. Why? Because this particular quantity is nothing but R, that is V is equal to IR or RI, and that R is being expanded and written as such, so that I can rearrange that equation and write it as V is equal to rho L I divided by A. So we know that I by A is nothing but current density. So we can write it as V is equal to rho L J. This is one more way of representing Ohm's law in terms of current density and resistance. So it can be written as such. And we are not stopping just there, because we know that V can be written as E into D, or in this particular case D is nothing but the length. That distance is the length. So we can write it as E into L. So instead of V, we are going to substitute E times L is equal to rho times L times J, which gets cancelled. Now we have an equation in terms of electric field. So we can write it as E is equal to rho J. So electric field of a material will be dependent upon the resistivity and current density of that particular material. Or you can simplify it even more and simply write it as E divided by rho is equal to J, but we know that rho is equal to 1 by sigma, which means 1 by rho is equal to sigma. So we can simply write it as E sigma is equal to J. And that is one more relation regarding electric field, conductivity and current density. That is all about resistors and Ohm's law. But the important thing to remember is that the scientists who have found and studied Ohm's law gave a condition, that is at constant temperatures, that if the temperature of a substance changes or the conditions of temperature change in your experiment, then the resistance value will not be a constant. It will fluctuate and Ohm's law will not hold. That particular graph which we found out to be a straight line won't be a straight line anymore. Why that happens and to which materials that happen will be discussed in the coming classes. So until then, I hope you have understood everything about resistance and Ohm's law. And one more thing to remember is that the unit of resistance is nothing but ohms, indicated by the capital letter omega. And it is known as ohms. Resistance, the unit of resistance, the SI unit of resistance is called ohms, as we are paying homage to a great scientist who studied Ohm's law and who proved Ohm's law. So G.S. Ohms is the scientist that we are paying tribute by giving the SI unit as ohms, and the letter or the symbol indicating that particular resistance is omega, that is capital Omega, indicated by such. So I hope you have understood everything about Ohm's law and resistance and how it is relating to different quantities. So until next class, I'll see you again with limitations of Ohm's law and temperature dependence. Until then, have a great day. Bye. Thank you.